Hello, and welcome to this series of lectures about variations on the Turing machine model, the Church-Turing thesis, and undecidability of the halting problem. I've been asked to introduce myself. I'm Eric Allender. I'm at Rutgers University, and I've also been asked to say a little bit something about my background and how I happened to end up in the field of complexity theory. I grew up in a small town in Iowa, Mount Pleasant, Iowa, and when I went off to college, I was very sure I wanted to be a theater major and started off studying theater, but I also, just as a backup plan, decided to double major in computer science because I'd been exposed to some computers as a high school student, which was not so common in Iowa in the 1970s, but I had a great math teacher who had brought a computer in and let us play with it. And so I had enjoyed that, and I always liked math, so I figured, why not be something to fall back on. But then I discovered the theoretical courses in computer science. They really fired my imagination. It convinced me that there was really cool stuff going on, and I got some encouragement from professors and applied to grad school, went off to Georgia Tech, and it's been a love affair with complexity theory ever since. I've been at Rutgers basically my entire professional career. I'm a former chair and getting close to retirement now. What do I work on? I work in computational complexity theory, the study of different complexity classes, especially subclasses of P, but also larger classes, and circuit complexity, Kolmogorov complexity, and lately focus of my attention has been the minimum circuit size problem. It's a problem actually fairly closely related to Kolmogorov complexity. Both of them ask, given a string, how hard is it? How much information is in there? Or how hard is the truth table represented by that string to compute as a function? This is something that is going to be intractable if cryptography is ever going to be a reality. But there are various obstacles that seem to stand in the way of our proving that it's NP complete. And it's interesting for a lot of other reasons. And I'd be glad to talk to people about it at greater length at another time. But it's time now to start reminding you what you should have learned from previous lectures, and also to have a preview about what lies ahead. So with luck, this is a picture that should look sort of familiar. This blob here represents the Turing acceptable languages. These go by different names. Sometimes they're called the recursively enumerable sets. Sometimes, since recursively enumerable has got a lot of letters, we just call it the RE sets. And back when I was a grad student, that's what they were called. But then shortly thereafter, people decided, you know, the word recursive is kind of a bit of a pain here. So why don't we call them computably enumerable? Highlight the fact that it has something to do with computation, and that would be abbreviated the CE sets. But a lot of people didn't get the memo about that, and so they still call them the recursively enumerable sets. And I'm likely to use any of these terms and not be entirely consistent, so be prepared for that. And one thing that I hope you learned from the last lecture was that the decidable sets occupy this very interesting region. Something is decidable if and only if it is both recursively enumerable and co-RE. And the decidable sets are sometimes called the recursive sets. So the co-RE sets are those sets that are the complements of the RE sets. And that is the region we're talking about. Part of my lectures will be to explain why these classes of sets really do capture an important part of any kind of notion of computation that you're likely to actually run across, no matter what that model of computation might be, as long as it looks something like programs. And also, we will be highlighting the existence of a few problems over here in this region that is things that are Turing acceptable or recursively enumerable and not decidable. And we will see some important examples of things that are not computable. So fasten your seatbelts. That's what lies ahead of you for the next few lectures. Until then, bye-bye. Hello and welcome back to the first real lecture in this series, where I'm going to now be talking about variations on the Turing machine model and why it's robust and why it's in fact a reasonable model to study at all. So in order to discuss that, let's take a look at what the model of Turing machine is that you've been looking at. Probably looks something like this. You have this infinite tape that has some input written on it, and you've got this box that walks around and reads and writes on the tape. So that's one possibility, but maybe what you've been exposed to, depending on what text you're looking at, looks more like this, where you have a two-way infinite tape, where everything else is the same. This is clearly no less powerful than the one-way infinite tape model, because if you just have a two-way infinite tape and you want to simulate a one-way infinite tape, you can just ignore everything that's to the left of the input, and maybe in fact you find it convenient to mark that spot so that you can also simulate the situation of falling off the end of the tape, so you can make absolutely sure that there's no difference in these models. But how about going the other way? Well, this is also pretty easy to see. If you consider that the tape might just as well be viewed as sort of a fat tape that can store a lot of symbols, maybe a pair of symbols instead of just one symbol. And let's say that you were simulating a computation using a two-way infinite tape that started and moved over here onto the part that's to the left of the work tape. Well, now you can simulate that using computation where instead you go over here and, oh, here's the end of the tape marker. So I just go up here and continue going in this direction where that top part of the fat tape is just viewed as the tape that had been going infinitely off in the other direction. So you can think of this sort of like a folding carpenter's ruler, where you can just take this part and move it, flip it over on top. So that's a pretty easy, simple idea, and maybe not even the most interesting variant that we might want to consider. Later on, we're definitely going to need to be talking about multi-tape Turing machines, particularly when you start talking about complexity theory. And a multi-tape Turing machine is just what it sounds like. You've got another tape sitting here, and I'm going to go ahead and make that have a couple of rows where you've got some. You can use this as workspace and do some writing there. And maybe you've got several tapes. Again, this is certainly no less powerful than just having one tape. And going the other way, if you've got a multi-tape machine, you can simulate it using a one-tape machine by, again, just doing the same silly idea of viewing your tape as being a fat tape. So put all of this sort of on just one fat tape, and these heads can move around and read both of them. And we'll also mark certain cells as being the ones that are currently being scanned. And in order to simulate a single step of the multi-tape machine on this machine with one fat tape, what can we do? We can just scan all the way across and see what is being scanned by each of the symbols. And then after I've seen what all of those heads are scanning, then I can move back across the tape and do an update, let's say moving that head that direction, moving this head to the other direction, and changing symbols as need be. So again, a very simple change, and again, perhaps not extremely interesting. So what's a more interesting variant of the Turing machine model? We're certainly going to be very interested in the non-deterministic Turing machine model, which, since you've studied finite automata and push-down automata, you're by now familiar with the non-deterministic model. And you can think of a computation on a non-deterministic machine as proceeding something like a tree. Here's your initial configuration, and let's say that there's 2 next moves possible for any step of the machine. And for any configuration, there's going to be, let's say, 2 possible next moves. And so you have this tree going on like that. And if there is n that leads to an accepting configuration, a halting accepting node, then we say that the non-deterministic machine accepts its input. So in terms of language recognizers, it's pretty clear what you want to do with non-deterministic machines. It's not so simple and elegant to talk about non-deterministic machines computing functions. So when we talk about non-deterministic machines, it's usually in the context of these yes or no questions. Is an input in the language or not? So how would we simulate a non-deterministic machine deterministically? It's a very simple idea. We're just going to explore that entire tree. We'll have one tape that starts off with our input on it. And the very first thing we're going to do is copy that input onto the work tape. And down on this third tape, we're going to enumerate 0, 1 star. So, we'll start off with a 0, and then we'll replace that with a 1, and then we'll replace that with 0, 0, etc. Looking at all of the possible strings over the alphabet 0, 1, and this corresponds to searching through the tree. So 0 corresponds to moving to the left. So 0 corresponds to this computation path of length 1 that just takes the rightmost branch. And if that leads us to an accepting path, then we'll say, okay, we accept. Otherwise, we look at 1. And if that leads us to an accepting path, we say we accept. And otherwise, we go over here. 0, 0 would correspond to that path. 0, 1 here, etc. We just try one after another all the paths of length 2 until we will have checked to see if any of the configurations at that node are accepting. And after each time we explore things, we just erase whatever we had on this work tape and with our input, because we have this input sitting up here at the original input tape, just handy dandy to use for that reason. And so we just explore the entire tree, and if there is an accepting path, we will eventually find one and halt and accept. And so great. Unlike with push-down automata, non-deterministic Turing machines and deterministic Turing machines both give us the computably enumerable sets. So perhaps a more important question you're seeing after seeing these symbols is, why Turing machines at all? why don't we base our model of computation on something like Java or C++ or Python or something else that's, you know, a little bit easier to program in than Turing machines? Well, sure, you can do that. You know, any of these programming languages, of course, have a language description manual that's a few hundred pages thick. And so it's not going to be as easy to describe what's going on as with the description of a Turing machine, which in some sense is like the original reduced instruction set computer, because there are not very many instructions there for you to use. But we're not going to prove this in detail, but it's not very hard to see that anything that you can write a program in one of your favorite programming languages, you can write something with the same input-output behavior in any other programming language, including Turing machines. And, you know, you can, let's just sketch a little bit about what's going on. Let's say that you wanted to simulate a particular program. You know, what is that? That's a finite length list of instructions with various control moves through it. And what motivates the flow of control in the program? Well, it's based on the data. And if you store your data on the tape, let's say you've got a region for any particular variables that you've stored, and you just know how to locate those variables, and you're walking around on the tape, you read what's there, and maybe it says, oh, copy the value of one variable into another. Well, we know how to do that on Turing machines. Maybe you do a subroutine call. What would you do to implement a subroutine call? Well, you'd walk all the way over to the blank portion of the tape, and you'd copy your arguments to the procedure here, and then you would put a little marker here so you'd know what part of the tape is legal to use for the subroutine. And then just using your finite control, you'd jump to the code for the subroutine, you'd start executing it, and then when it had completed, you'd go back to where you had been before, where you had information marked. It's a boring exercise, but a routine exercise to translate anything you can do in your favorite programming language to Turing machines. Our next lecture is going to touch on maybe the more interesting question about why we still use this particular model, the Turing machine. What was Turing's motivation, and what is the church Turing thesis? That is the topic of our next lecture. Bye-bye.